Hi everyone, welcome to another video by Cheenta. I am Rajdeep, and this is the new installment in the ongoing number theory series. Last time we saw a few things about arithmetic functions, in particular the Euler totient function, and I left you with Gauss's lemma, one of the many results with that name. Today we'll start there and use the wheelhouse of results to prove a very interesting problem from the IMO 2004 shortlist. Those of you who don't know what the IMO shortlist is, I'll get into it later, but it's a very hard and nice problem, and we'll develop tools today to help us solve that. So let's get into it. So in front of you is the problem in question from the IMO 2004 shortlist. N2. So the way these shortlists works is that, as you may know, the International Mathematical Olympiad is a 6-problem test. 6 problems spanning over many hours, and those are hard problems. And what the shortlist is essentially a semi-final list of problems, in that every country submits its set of problems that they want to propose to the IMO, and those problems end up in the long list. That's not been public for a while, many years, but the short list is made public every year after the IMO. And the short list consists of all the problems that the committee selects in a semi-final list. And they are usually broken up into algebra, geometry, number theory, and combinatorics. And each section of each topic has problems with a sort of an ascending order of hardness. So N1 is the easiest number theory problem, G1 is the easiest geometry problem, and so on. And usually it goes up to G6, G7, G8, N6, N7, 8, 8, and so on. Roughly 8 problems per topic. So this is N2. It's the second problem in the number theory shortlist from 2004. So it's not particularly easy by any means. And I should say that the problem in front of you is not the complete question. It is only part A of it. There's 2 other parts, but they are too big to get into. After all, it's a hard IMO problem. But I will only look at part A, and that in and of itself is also very interesting. So this is the question. It was proposed by Russia, so that's always a good thing. Russian problems tend to be very interesting and very offbeat, so that's always a good sign. The function psi from the set of natural numbers to itself is defined by the equality psi of n is equal to the sum over k is equal to 1 to n of the GCD of k and n, where k comma n means the GCD of k and n, as is written down here. So you just sum over the numbers from 1 to n and look at the GCD that they have within, and you just sum all of them. It's a very interesting function to think about. And we want to prove that this function c of n is actually multiplicative. If you remember that was the definition of multiplicativity. So this interesting looking function, we want to prove that it's multiplicative. Instead of directly getting into the problem, I will take a theoretical route to it so that it builds naturally, but feel free to pause the video and try the problem on your own. Hopefully you've tried it and you've gotten a feel for it. You might even have noticed some similarity with the kind of functions we've been working with over the past couple of videos, but I'll leave you with those thoughts to yourself. Last time, I wrote down Gauss's lemma on the board, one of the many, which said that if phi is the Euler's totient function, and as you may see, the function c defined by the problem has something similar to do with phi. If you recall, Euler's totient function was the number of phi of n was the number of positive integers between 1 and n, which are co-prime to n. And so this is of a similar flavor, the function in the problem, because it has something to do with the GCDs as well. So that's phi, and we had that sum over phi of d, as d runs over the divisors of n, is actually equal to n. I didn't give a proof last time, but I will this time, and I will generally look at constructions of these type. So a quick proof of this is very sweet. It's a very classic proof in number theory. in these parts, and it's very sweet. The way it works is you look at these fractions 1 by n. So obviously, if you fix n at first, and you look at the fractions 1 by n, 2 by n, 3 by n, all the way up to n by n. We can even look at n minus 1. It doesn't really matter. But n by n just gives you a more immediate result. So you look at these n fractions, right? And you reduce them, by which I mean wherever there's a common factor in the numerator and denominator, you cancel it out. And after you do this process, you get some n new fractions. But think about it. What are the denominators in these fractions? There are obviously going to be some divisors of n, right? So the denominators that show up in this new list of fractions are just divisors of n. So you can obviously ask the question, how many times does a given divisor show up in a denominator? Or you can flip the question, how many fractions will I see for a given denominator? So for a fixed divisor d of n, how many fractions show up in that list? And the answer is very simple. And you might already expect the answer. Phi of d, right? Because the only way you get something of the form a by d which does not reduce further is if a is coprime to d. So for every number between 1 and d, which is coprime to d, we will get a fraction. And it's a fraction between 1 by n and n by n. So it's very nice. So you really just get a sum. So at this point, the result is clear that the number of fractions, so the number of fractions, which we already know to be n, is actually also equal to the sum of phi of d as d runs over the divisors. Very nice. It's a very sweet proof. But this does beg the natural question, which is, given a multiplicative function, multiplicative arithmetic function, but we don't write it, over and over again, function f from n to whatever, n, real numbers or complex numbers, let's say real numbers. If I consider the function f of n, capital F of n, which is the sum of the values of small f, our original function, at the divisor of n. We sum them. Very similar to the construction we just saw. What can I say about this guy? In particular, what he can always say is that generally I can always say f is multiplicative, which is surprising. That whenever you have a function of this form, I can always say it's multiplicative, given that obviously this guy is multiplicative. Why is that? I won't get into an exact proof. I will only give an outline. The point is that if m and n are coprime, and if I want to talk about this guy, this is nothing but sum over d divides mn of f of mn. But since f was multiplicative, this is fm times fn. Since I start with m and n that are coprime to each other, right? That's the premise of multiplicativity. D divides mn. And now the main trick is that a divisor d of mn just neatly splits into a divisor of m and a divisor of n because m and n are coprime. So you can write this as a product of sums. F of m d divides n, f of n d divides n, which is just f of m times f of m. Hopefully that made some sense. So whenever you start with a multiplicative function and you apply this transformation on it, you always get a multiplicative function. That's very nice. What you just learned is, given a multiplicative function, I can always make a new one. Multiplicative function, I can make a new one, which is always exciting because you have a new tool in your toolbox. And also, this is sometimes a very easy way of proving that a given function is multiplicative. I can make a new one. Yeah. But you can do better. And we'll get into that, and that's the topic of Dirichlet convolutions. But before I do that, I do want to sort of point a couple of things out. What we just saw lines up with what we saw before. The function n, which is, it just sends n to itself is obviously multiplicative. So this holds up. But we can do more interesting things. We get that this function, d of n, the number of divisors, right? Sum of 1, the identity function 1, right? 1, d divides n, is also multiplicative, right? Because, by the way, maybe I should clarify further, 1 is just this sort of block identity function. It just sends every number to 1, right? That's what d of n is, right? You just sum 1 for each of the divisors, you just get the number of divisors. Since this function is obviously multiplicative, you multiply two numbers, you get 1, since you start with 1. It's obviously multiplicative. But this proves that the number of divisors is multiplicative. Similarly, since the function f of n is equal to n is multiplicative, sigma of n, which is the sum of divisors, sum of d as d divides n, also multiplicative. So this kind of gives us these very quick fire proofs of the multiplicativity of these functions that we were looking at before. So that's very nice, and maybe you can play around with it a bit more. What Dirichlet convolution does is, given two multiplicative functions, I can make a new one based off it. It's simply a generalization of the construction we just saw. Given two multiplicative functions, f and g from n to, wherever, the natural numbers to real numbers or complex numbers, doesn't really matter. As long as they're both multiplicative, I can make a new function, which, you can write whatever, h, say. And it's defined as, running over the divisors d of n, f of d times g of n by d. D and n by d are like the complementary divisors of each other, right? In some way, right? D into n by d is equal to n, so you just get these complementary pairs of divisors. So why is this called convolution? The idea of convolution is very interesting. In some way, you're sort of matching complementary pairs of values of these numbers. So stuff like this shows up a lot. In some way, this is also very similar to the other kind of convolution that you get sometimes, which is f of x times g of 1 minus x. You might have seen integrals of this type in your work, whatever your work is, or maybe you haven't. This is a very classic sort of thing, and you can interpret it in many ways. But for now, we will not get into the idea of convolution in general. This is just a nice construction, and we write it as f star g. Star is like an operator, sort of. Star is a thing that takes two multiplicative function and spits out another. I will not prove this, but f star g, which is defined as, this sum, it's a construct, is also multiplicative. It's a very nice result. But before I get into the other properties of star, let's go back to our original problem. It's much simpler now. Let's try to understand what this is. We'll use the same approach we used a little while ago, which is what numbers show up here. What are the numbers that show up as GCDs of some number less than n and n? They're just divisors of n, right? Because it's a common divisor of something and n, it is at the very least a divisor of n. So I know that since I'm looking at this function c, or psi, so the GCD of k and n as k runs over 1 to n, I know that this is a divisor of n. So I can ask the question, how many times does each divisor show up? Show up as, k comma n, for some k between 1 and n. Obviously, if you want some, so let's fix d. Let's fix some divisor d of n. If I want d to be k comma n, at the very least, I know that d has to divide k. So k is of the form d times n. It's a multiple of d, right? Otherwise, it can't be a common divisor of d and n. Now you have d times something and n. So without getting too bogged down in technicalities, I will say that this can only happen if and only if L is coprime to n by d. Right. Why is this? Is because I kind of don't want any new factors of n to show up in L, if that makes sense. D is already a factor of n. Now, whatever is remaining, I don't want it to show up in the common divisor. So whatever L is, I don't want it to share any new prime factors with n. So what are the new prime factors that it can have with n, which already aren't in D? What are the primes, if you will, that show up in n but not in D? Exactly the primes in n by D. So I don't want L to have anything to do with n by D, because otherwise it will show up in, like, it will add to the pre-existing GCD, which is D, in some way. You can sort of start by imagining the GCD is D, and now depending on L, GCD might grow. D is like the baseline, and depending on what L is, it might be larger. If I want to stop this growth at D itself, I want to make sure that no new prime factors get added. And the only way to do that is to make sure that L has nothing to do with n by D, otherwise it will add to it. And so we really just want to know how many numbers like L are there. I can just multiply it with D, and that's how I'll get all the K, right? For which K comma n is equal to 1, is equal to D. But how many numbers are there which are coprime to n by D and are less than n by D, obviously? Phi of n by D. So I get that D shows up this many times. Hence, my sum of K comma n, K is equal to 1 to n, is actually just sum of D times phi of n by D. D runs over the divisors of n. As you've seen, this is a Dirichlet convolution, right? D is just, this is just the identity function, in that this corresponds to the function f that just sends n to itself, right? F of D, so I can write this as sum of D divides n, f of D times g of n by D, where f is just the simple identity function and g is phi. Both of these are multiplicative, hence the Dirichlet convolution C of n is also multiplicative. And that solves part A. I could stop the video here and more or less we're done. I do want to talk about what the Dirichlet convolution, what properties it has. In some way, this Dirichlet convolution functions as a multiplication. In some way, it already kind of looks, it already has the multiplication of natural numbers built into it. This is a multiplication of functions in some way. And it has a lot of incredible properties. One of which you've already seen is that it takes two multiplicative functions and spits out a new one. It is also commutative. F star g is equal to g star f. That's actually pretty easy to see. It also distributes over pointwise addition. And best of all, there are inverses and identity, which I will not get into, but in some way, there is a function that I can make up. It's not very hard to make up. It's called the Dirac delta or the Dirichlet delta, depending on who you ask, which is just 1 at whatever point you're looking at. So delta is a function which is just delta of n is equal to 1, and it is 0 everywhere else. So it just peaks at a single value and 0 everywhere else. This is the identity. If I convolve it with any function, I'll just get the function back. So this functions as the identity. Wherever there's an identity, you should ask the question, do I have an inverse? F star g, which is equal to del. And this is where the Mobius function comes up. If I ask the question, what about this function, 1 of, which just sends n to 1, everything to 1. And if I ask, what is the inverse of this, right? Why would I ask this? Because in some way, I had defined f of n, capital F of n, as this sum, right? Which is what? It is just the convolution, or Dirichlet convolution, of f with this function, right? The big 1 function, right? And so if I could somehow flip it, if I could somehow take an inverse I get that capital F is this. If I could somehow take an inverse, I could actually write F as a function of capital F. So this gives me a way to talk about, small f completely in terms of capital F, which can be very, very helpful sometimes. So this is where the Mobius function comes in. A Mobius function, which I will not define, I'd urge you to look it up, is a function which has the exact property that mu Dirichlet convolved with this function identity is delta. It's the inverse of this one function. And because of this property, we get something known as Mobius inversion, which is a very cool result that I will not get into. But this is kind of the basis of the Mobius function. If you look it up, what Mobius function is, it may seem a little bit arbitrary. It's more or less natural. But whatever arbitrariness is, this is a very natural line with which you can define the Mobius function. And this is also why Mobius inversion is as cool as it is. But I will not get into that today. I hope you enjoyed the video. Thank you very much for watching. Bye-bye.